December 17, 1903, Kitty Hawk, North Carolina. When Wilbur Wright spun the propeller and his brother Orville took the controls, man's first powered flight in an airplane began. A flight that changed the course of the history of the world. A short time later, another great American pioneer, Glenn Curtiss, built and successfully flew the world's first seaplane. Just as the names of the Wright brothers and of Glenn Curtiss are linked inseparably with the beginning of flight, so too is the organization that bears their names linked with the advancement of flying. For the exciting story of aviation is the story of Curtiss Wright and the products of its research and engineering. 1909, Wright builds the first airplane for the U.S. Army. (1911) Curtiss builds the first airplane for the Navy, which was flown off the USS Birmingham and landed on the Pennsylvania. 1917, Curtiss Jennies train America's fledgling Air Corps. 1918, Curtiss builds the first airmail plane. 1919, the Navy crosses the Atlantic in the Curtiss NC-4. 1926, the newly developed Wright Whirlwind engines carry Admiral Byrd over the North Pole. With this revolutionary radial air-cooled engine, modern air power was born. 1927, a Wright Whirlwind engine carries Charles Lindbergh across the Atlantic Ocean. 1932, the more powerful Wright Cyclone engines fly the first Douglas airliner and become the world's standard transport engine. 1934, the Curtiss Condor, the first passenger sleeper plane. 1936, Wright Cyclone engines chosen by the Army to power the new 4-engine Flying Fortress. 1938, Curtiss develops the famous V-36, starting a new trend of high-speed, hard-hitting fighters, the fighters which were so soon to be called to the aid of democracy in Europe. 1939, Pan American Airways starts regular transatlantic passenger service using Wright engines. 1939, the German Army attacks Poland. Europe goes to war, and America strains to arm herself for defense. The next 2 years at Curtiss Wright saw a great expansion program take shape. New plants were acquired or built in record time. New personnel was trained and put to work, and the output of airplanes, engines, and propellers multiplied. And well that it did. The thing that was going to win that fight was production, and still more production. Curtiss Wright was called on for a greater share than any other organization in the industry. Starting with 3 plants in 1939, Curtiss Wright was operating 19 at war's end. starting with 8,400 employees, the company increased its personnel to 185,000. During World War II, Curtiss Wright was the largest producer of military aircraft in the nation. Here are some of Curtiss Wright's contributions. The famous Curtiss P-40, used by General Chennault's Flying Tigers. It was the only available American fighter at the outset of the war and was used on every fighting front. The Curtiss Commando, the C-46, a great cargo carrier. It flew the hump and kept China supplied when the Burma Road was closed. The Curtiss Helldiver, the Navy called this dive bomber its Sunday Punch. Curtiss electric propellers were used on practically all fighter planes. Wright Cyclone engines powered bombers such as the B-25s of General Jimmy Doolittle on his Tokyo raid. B-17 Flying Fortress that knocked out Germany. It was powered by Wright Cyclones. Still bigger Wright Cyclones were built under forced draft to power the great V-29 superfortresses which carried the aerial war to Japan. These Wright engines with Curtiss electric propellers were chosen for the most important mission of the war, to carry the V-29 that dropped the atom bomb on Japan and ended the conflict. But what of peace? "19 Curtiss Wright plants going full blast on war production, and suddenly they aren't needed anymore." This was an even more difficult test of good management than the sudden demands made by Pearl Harbor. Curtiss Wright's record of reconversion and recovery is unequaled in the industry. Streamlining was the answer. Tighten up the belt, conserve resources, get rid of unneeded plants, reduce personnel, but keep a skilled nucleus. Engage only in profitable phases of the business. How well this streamlining has been done can be seen by visiting today's plants. In its propeller plant at Caldwell, New Jersey, the largest and most modern in the country, Curtiss Wright produces more propellers than all other United States manufacturers. These propellers, made of the finest steels, are rugged, able to withstand the enormous stresses of modern flight. And at the same time, they are marvels of precision, well balanced and accurate, like an expensive watch. A single blade costs many thousands of dollars, such as this 19-foot propeller for the huge new B-36 Super Bomber. It's the largest airplane propeller in the world. This one is for a new bomber, the B-50. The pitch of this propeller can be completely reversed by electric power. On the ground, the pilot can now use the engine to slow down the plane instead of using his brakes. And he can also back the plane up by reversing the pitch of the blades. This feature is a great advantage in landing and in handling planes at the airport. But a revolutionary application of this propeller has recently been demonstrated. Here, the thrust of the propellers is being reversed while the ship is in flight, making it possible to greatly increase the rate of descent without increasing the forward speed. In an emergency, a plane could land from 10,000 feet in a minute instead of the 7 minutes that are now required. Furthermore, once on the ground, the plane is slowed down to a standstill by the reversed propellers. testing, experimenting, testing, trying out new ideas. That's how the modern propeller was born. That's how the propeller of tomorrow and the day after will be created. It was this kind of pioneering research, as carried on by the Curtiss Wright Propeller Division, that resulted in the development of an amazing device, the Curtiss Wright Electronic Flight Simulator, which has been called one of the most fundamental advances in flight training in the history of aviation. This marvelous unit is operated electronically and is identical with the interior of the plane's cockpit. Without leaving the ground, it can reproduce any condition of flight of which the airplane itself is capable, and just as the flight instructor decides, too. It realistically reproduces even winds, weather, temperature, atmospheric conditions, and duplicates radio communication and navigation factors. Here, for instance, the problem board is set up to simulate the condition of ice forming on the wings of the airplane. The captain and his crew actually learn on the ground how to correct any problem which may occur in flight. Lessons thus learned are vital to safe and efficient flight operation. The value of this unit in training flight crews has been quickly recognized by the airlines, and the military air forces already have placed an initial order amounting to more than $2,500,000. The streamlining of the Curtiss Wright organization was carried out in the Airplane Division, which is now concentrated in a modern plant at Columbus, Ohio. Unprofitable contracts were canceled and various projects undertaken that would keep a smaller organization intact. Like, for instance, the manufacture under subcontract of urgently needed airframe sections. Here, too, an extensive program of rebuilding battle-weary Army and Navy transports has made it possible to retain many skilled employees. This was done in a period when these men would otherwise have been laid off. Another project that accomplishes this objective is the manufacture of droppable fuel tanks for both the Navy and the Air Forces. 10,000 of these units have been manufactured so far. In addition, 3 non-aviation companies, readily convertible in time of emergency, were taken over and put to profitable work. These are Marquette Metal Products in Cleveland, which makes precision parts, the LGS Spring Clutch Division at Indianapolis, which makes a highly useful clutch for industrial purposes, and Victor Animatograph at Davenport, Iowa, which makes motion picture equipment. These activities have been carried on, of course, while Curtiss engineers have been planning for the future. Constant research and development work is part of the basic policy of the company. A good example of forward thinking is the development of the CW-32. This blueprint in wood is an exact pattern of a revolutionary new airplane, a first attempt by the aviation industry to design a heavy-duty truck for the carriage of freight along the highways of the sky. Capable of carrying cargo at lower rates than even railway express, it was designed to help the airlines develop great untapped volumes of air freight business. This ship was designed to receive cargo through its side door and also through the tail. The revolutionary idea has aroused tremendous interest in the industry and also in the military services. The largest of the Curtiss Wright divisions to be streamlined is the Wright Engine Division, now located in a new, modern plant at Woodridge, New Jersey. The engine is the most important and complex part of an airplane, and during the war, Wright built over 138,000 of them for the armed forces. The division today has 6,800 people turning out greatly advanced 7, 9, and 18-cylinder power plants for our peacetime air forces and for the civilian airlines. The list of users of Wright engines reads like a roster of the world's airlines. TWA, American Airlines, Eastern, Delta, Capital, Colonial Airlines, Chicago and Southern, National Airlines, Pan American Airways, British Overseas, Air France, KLM, the Royal Dutch Airlines, Sabina, Belgium, Aviation, yes, Mexico, the Australian National Airlines, TACA, serving Central America, Swiss Air, Switzerland. Well, that's enough to show what professional aviation people think of the engine. Here's a striking example of the power in Wright engines. The flight engineer cuts one engine and feathers the prop, and the big 60-passenger Constellation flies smoothly along. He cuts another engine. That's not unheard of either, of course. But now he cuts a third engine, and the big plane continues to fly with only one propeller pulling it through the air. Dramatic proof of the margin of safety in airline travel contributed by the tremendous power and dependability in Wright's Cyclone engines. To this Cyclone, probably the world's most famous engine, Wright engineers have recently added the greatest power step-up in engine history. This near miracle was accomplished by harnessing the power in the flaming exhaust gases from the 18 cylinders. By means of a still secret turbine system, this power is geared back into the main propeller shaft. The result? An automatic increase of 20% in power with no increase in fuel consumption. This means that the transport planes of the future can fly 20% farther or carry a fifth more load than ever before. In military use, it means that today's bombers can be extended in range to cover half the world in a single non-stop flight. Throughout the Curtiss Wright organization, the air is full of new, promising developments. Into them have gone millions of dollars in research and engineering. More millions must yet be invested in their perfection for production. But from these test cells and from the Curtiss Wright laboratories are already emerging the forms of the future of flight. A great deal of this vital and expensive research and development work is secret. We can, however, with Uncle Sam's permission, catch a glimpse of a few of these exciting developments. The U.S. Air Forces selected Wright to design and operate the world's largest laboratory for the development of turbine engines. From this plant has already come the great T-35 Typhoon, one of the new Wright turbine engines, so powerful it is still a closely guarded military secret. To test it, Wright engineers designed this unique flying laboratory, which cuts to a fraction the time and cost heretofore necessary for flight testing a new engine. The laboratory is carried aloft by 4 conventional engines, then the giant turbine takes over. Even more secret are Wright's jet engines. Here a ramjet involving new principles is being tested. To speed development of this new source of flying horsepower, a special laboratory is being built. In the airplane division, we catch sight of another security-guarded project. It's a part of the frame of the world's fastest radio-controlled pilotless plane. A swift flying drone to perfect the gunnery of our aerial fighters. The United States Air Force's X-1, to be launched from this V-29, was the first plane to fly faster than sound. Today, engineers at the Curtiss Propeller Division are building rocket engines for the X-2, designed to explore speeds miles an hour already reached by the X-1. And at the Airplane Division, again engineers are constantly at work to perfect the means of guiding huge rocket-powered missiles. Only yesterday, these were Buck Rogers' dreams. But today, government and industry are putting millions of dollars into these completely automatic rockets, missiles which have already pierced the skies 100 miles above our Earth. Indeed, we have come a long way from the days of Glenn Curtiss and the Wright brothers. Curtiss Wright's president told me the other day that American aviation will make even greater progress in the next 10 years than was made in the last 40. That means greater opportunities than ever. Curtiss Wright intends to take full advantage of those opportunities to continue to merit its slogan of long-standing, first in flight, so that America will remain first in the air.